Let's go ahead and get started with this. I'm Mike Welfel. I'm a product manager here at ToloTalks, and the material that I've pulled together for you today is kind of a summary of top-level items to know and think about when you're designing servo systems and motion control systems for machine designs. So let's get started with it. Let's see here. There we go. So here's the topics I'm going to try and cover in pretty rapid succession here. So try and stick with me. I'm going to start out with the basic design of servo drives to give you an idea, kind of a new picture in your head for the sections of a servo drive and what parts are important to you as you're doing a machine design. And then I'm going to segue into specifically brushless servo drives. And some of you over time may have run into the term AC brushless or DC brushless or trapezoidal. And I'm going to try and quickly clarify the differences between those and how they relate to applying them on different machines. And then we're going to talk about encoders and resolvers quickly and try and give you a picture of the differences between those and how you might want to apply them differently. Same for steppers and servos. And then we'll dive just a little bit into the black magic of PID tuning, and I'll try and simplify that for you. And then the last item I have is just a couple of comments on applying high power servo drives. We're seeing larger and larger linear actuators used in industrial automation. And there's a couple things to think about with respect to applying those high power systems, and particularly in cases where you might not have suppliers that have high power servos. So we'll try and help you out with that. So let's get started with it here. So first we'll talk about servo drives. And what I do is I break servo drives into kind of three subsections: the power supply, the output section, and the control loops. And first I'm going to focus on the power supply section, and we'll kind of build on this to help you understand how any differences in applying different servo drives to automation systems. So first we'll look at the power supply. So the power supply for any servo drive is a rectifier system, basically an AC to DC converter system. And in some servo drives, this is a separate box, and in many others, this is built into the servo drive. Either way, you have to have a power supply for the servo drive. So the power supply is quite a simple device. It takes the AC, either 230 or 460 volt AC. It goes through a bridge rectifier where it's rectified, full wave rectified like that. And then it goes across a set of large DC bus capacitors. And those capacitors smooth out the signal to give you a DC voltage quantity. And when people talk about the DC bus, that's really what they're talking about, is the output of the power supply here. So that's what the power supply for a servo drive looks like, and that's what it does. And the power that goes from the servo drive goes to a set of transistors in the output section. So I'm going to start with a DC brush type servo drive because it's just a little bit easier to visualize. And then we'll go into what a brushless servo drive looks like. So a DC servo drive just consists of a set of 4 transistors, and they're connected to the DC bus, that power supply we just talked about. And the power from that DC bus is allowed to go through the motor in one particular direction when you turn on the upper left-hand transistor and the lower right-hand transistor. Current goes through the motor in one direction. And when you want to rotate the motor in the other direction, then you just turn on the other set of transistors. That's all a DC drive really does. There's other electronics that go around it, but that's the essence of it. So one thing that happens on a DC drive that's good to keep in mind, or on any drive, that's good to keep in mind when you're applying them on a machine, is what happens when the motor is decelerating. And when any motor decelerates, it becomes a generator, and that means the power must go back onto the DC bus. And what happens in servo drives is they just add a set of diodes, and you might have heard these called freewheeling diodes, that allow current to go back onto the DC bus. And this works great until you have so much current going back onto the DC bus that it increases the voltage of the DC bus up to a point that might damage the capacitors and other components. So this is where a shunt resistor is added into the system. And this is where we get into one of the first points that is helpful when you're talking about machines, is trying to keep in mind how much energy is being regenerated back onto the bus. So this right-hand side where you see this resistor that is getting heated up, that transistor is just a switch that turns on and allows energy to shunt across that resistor. That's what's happening when a drive goes into its regenerate, or when the drive has to allow for regenerated energy from the motor. And this is important to keep in mind when you're sizing your systems. And a lot of sizing software may not actually do the calculations for this. So you have to kind of keep in mind that. And it's particularly a problem on systems like printing presses or converting machines, where you have large steel cylinders or cylinders that have high inertia. And when they decelerate, they backdrive energy onto the system. So that's what a shunt resistor is and how it looks in a system. So one other thing you may have heard of relative to servo drives is something called PWM, or pulse width modulation. And all that is that it turns out that if you pulse transistors on when you're running current through the motor, instead of holding them on continuously, they generate a lot less heat. So pulse width modulation is just pulsing the transistors on, just the same as the previous pictures, and to determine the direction of rotation. But you can build a lot smaller servo drives because you're pulsing them on and they don't generate as much heat. So that's PWM. So let's go into brushless servo drives here. So this is our DC drive that we've just been talking about. And on a brushless drive, that's typically a three-phase motor. So what you need is an extra set of transistors and diodes that gets connected to the three-phase motor like this. Otherwise, everything else is the same. Even when it's back driving or regenerating, the power still goes back onto the bus, and you still need a shunt resistor. So with a brushless drive, you don't have brushes in the motor to change which coils the current goes to as it rotates around. So on a brushless drive, you need some additional commutation control that tells the transistors when to turn on and off. And you need some device to detect the position of the rotor on that motor that tells the transistors when to turn on and off. So that's the main difference between a brushless servo drive and a brush type servo drive. So also, when you're talking about brushless servo drives, there's two ways to create the waveform that goes out to the motor. If you use cheap Hall effect switches on the end of the servo motor to tell you what the rotor position is, you can create a trapezoidal wave like that waveform on the top there. And that is typically what people are referring to when they say a DC brushless drive. They're talking about a brushless drive that typically uses Hall effect feedback and creates a sine wave that is sort of choppy like that. So they call that a trapezoidal drive. Now, if you use an encoder or a resolver as your feedback device, you have a lot higher resolution and you can create a smooth sine wave. And that's typically what people are referring to if they say AC brushless drive. So those are two kinds of drives, two kinds of brushless drive that you have the choice of applying on your machine. So the difference when you're applying them is that the trapezoidal commutation has a significant amount of torque ripple that'll show up in the motion of your motor. So for example, if you're applying a servo drive on a machine tool where you want a lot of precision, smooth motion, you would not want to use a trapezoidal drive because it does have that additional torque ripple. The sinusoidal commutation, so AC brushless servo drive, is much smoother, so it doesn't have that torque ripple. So that's kind of the differences between the two kinds of brushless servo drive. And just to give you a little bit deeper insight into the performance differences between different kinds of servo drives, here's a comparison of this measurement quality called speed range for different kinds of drives. So some of you may be familiar with SCR drives. That's an older drive technology. And you can see that the measurement of low speed performance is like 50 to 1 on an SCR drive. For a variable frequency drive, it's 200 to 1. And then for a vector drive, it's 1,000 to 1. And then a PWM servo drive is like 8,000 to 1. So you can see that you get a lot better low speed performance when you use a servo drive. And the same thing happens with another parameter called speed regulation, that when you're measuring your no load speed versus full load speed and looking at the variation, then a PWM servo drive over its entire speed range is going to hold its speed, its set speed, much more precisely than any of these other servo drives, or not servo drives, but any of these other drives. So that gives you an idea of how much better a servo drive is at performing the motion for a motor. So now let's dive into encoders and resolvers. So most of you probably kind of have this picture of an encoder where it's like a glass or a steel disc, and you've got a LED transmitter, and it's going to a photo transistor and receiving the signal, and the output of the encoder, is steps like this. So the faster the steps come, the better ability you have to measure your speed. So what happens on encoders that is also good to keep in mind is that every encoder has a zero marker pulse, or most encoders do for servo drives. And when you're homing a servo system, you're probably familiar with the limit switches that are put on systems. But a system doesn't usually use the limit switch as its final homing reference. It uses the zero marker pulse as its final homing reference. And what that does is that if you have an encoder that has 10,000 counts per revolution, that means that your final position that you home to is within 1/10,000th of a revolution of the motor. So you get very precise homing when you home to the limit switch, and then it looks for the zero marker pulse after that. So also on encoders, the actual design of them is a little bit more sophisticated in that what happens is there's actually two light sensors that pick up the light source, and they're 90 degrees out of phase with each other. So what that gives you is a encoder output that has two channels that are 90 degrees out of phase with each other. And the beauty of that is that allows you now to tell the direction you're rotating. Because if you imagine you're a little stick person on the left side of the screen here, and you're walking towards the pulses, you would run into the top pulse first if you're coming from the left-hand side, but if you're coming from the right-hand side, you run into the bottom pulse first. Hopefully that kind of gives you a picture of how it works. But by detecting which pulse is leading or which channel is leading the other using some fairly simple electronics, that's how we can figure out the direction of rotation of an encoder. So that's called quadrature. So that's why there's two channels, channel A and channel B, on encoders going into servo drives. Then the other thing that happens with encoders is you have a choice of output types. And the basic choice is between line driver outputs and open collector outputs. And typically, if you can, you should use line driver outputs because they drive the line in a specific state, whether it's high or low. Open collector outputs can have a floating state. So line driver is the preferred choice when you're choosing an encoder, if you have to choose one at all. And then the other thing that happens with encoders is you may have seen how they have an A channel and an A naught channel and a B channel and a B naught channel. And the reason they do that is that you can take the A and A naught channel and transmit them over a distance. And then since they're twisted pairs, any noise that is received by those cables is received the same on both the A naught and A channel, and you can subtract them from each other and basically eliminate the noise. So that's why on encoders you see that they have A and B channels, but they also have A and A naught channels. So definitely preferable to use differential line driver encoders whenever possible. So getting into the different types of encoders, particularly absolute encoders, the disk you see on the left here is an incremental encoder. So it just has the pulses going, or slots going around it. If you want to measure the rotation of your motor, or you want to know where it is specific within one rotation, you need a different kind of way to do that. And one way in the middle of the screen here is an absolute encoder disk that actually puts out like a binary or BCD value. And this works well, except that you need one set of wires for each of those tracks. So you can imagine if it's a 12-bit track, you need all wires for all 12 of those, and you probably need the differential, so the A and the A naught for each one of those. So these have lost popularity just because the cables get so big. Over on the right are two other ways that manufacturers have evolved to create absolute encoders. The one on the top is a geared absolute encoder. So that way they kind of do what that expensive disk in the middle does, just through a bunch of gears, and you can know where your encoder is within one revolution. And many times these encoders will allow you to have absolute position within a high number of revolutions, say 4,000 or 16,000. Then the other way to do this is using battery-backed encoders. And this has become quite popular now, with the improvements in battery technology, now that they last so long and are low cost for good batteries. And that does tend to be a little bit lower cost encoder system than the geared encoder system on the top there. So you probably see those, and in general, I think that there's not really any performance differences between battery-backed or geared encoders for absolute encoders. But I do think that when you see battery-backed encoders, they do tend to cost a little less. So that's encoders for servo drives. The next thing I want to get into to help you differentiate between encoders and their counterpart resolvers is to try and give you a little bit of a picture of how resolvers work, and then show you the performance differences between these two technologies. So this is my Fred Flintstone picture of a resolver. And the way it works, if you look on the lower left here, is that we input a sine wave into this orange disk here that is a circular transformer. And so that orange disk is stationary, and the blue one behind it is fastened to the rotor of the resolver. And the sine wave just gets inducted onto those two black wires near the shaft of the resolver there. So you just get a sine wave going into the kind of dark blue rotor of the resolver. And then that again transmits those sine waves to the stator of the resolver. So it seems kind of complicated, but actually from a manufacturing standpoint, it's quite simple. There's really simple windings, and there's no electronics in this, so that your ability to withstand heat is much higher, and your ability to withstand shock and vibration is much higher than an encoder with electronics and circuit boards and so forth in it. So that's roughly how a resolver works. You put a sine wave into it, and you get two sine waves out of it, and those sine waves are 90 degrees out of phase. So to dive a little bit deeper into what happens, hopefully this isn't getting too complicated on this picture here, but what happens is the sine output and cosine output look something like these black lines here. And if you look at the peaks of these, then you can get a signal that looks like this here. So out of the sine output and cosine output. And what that does is that they have a different value for anywhere over the 360 degrees of revolution. And that means you have a absolute feedback device over one revolution. And so what manufacturers do is they measure the value of the cosine and the sine with high resolution analog to digital converters. And what that does is then it gives you a very high resolution way of measuring the rotation over one revolution. So even though these sine waves, you just get one cycle over one revolution, when you measure it with an analog to digital converter, you can get a resolution as high as, say, 16,000 counts per revolution or maybe higher. So that's how resolvers kind of work, the Reader's Digest version of how they work. And the one additional piece you need with a resolver system is you need a resolver to digital converter chip. And this usually resides in the servo drive. And so that generates the rotor excitation signal, and it receives the sine and cosine signal, and then it communicates the position back to the motion controller. Some folks have, I think, recently created really robust digital converter chips and actually put them on the back of the resolver and use just a two-wire serial, high-speed serial communications interface to implement single cable feedback. So some people are doing some different things with this, but this is the fundamental system. So what are the differences in performance between resolvers and encoders? Well, over the years, both of them have improved remarkably, but there's still some pretty significant differences in them. So if you look at the accuracy of an encoder versus a resolver, you can see that an encoder, trying to compare high-end resolvers and encoders, an encoder is still about 5 times more accurate than a resolver is, just because a resolver is really a mechanical device. So the accuracy is related to how well you wind it and manufacture it. Whereas encoders, the disks on them are sometimes printed using semiconductor printing techniques, so you get super high resolution and accuracy. Then the resolution, the number of steps per rev you can get out of these has also a big difference. Both of them are very high, but out of some encoders, you can get up to 2 million steps per rev, whereas resolvers, you might get 65,000 steps per rev. Then where you do see some significant differences is in the shock and vibration. So a resolver, of course, can withstand a lot more shock, and same with operating temperature. So that kind of gives you a feeling of, when you're trying to decide if you want to apply a resolver encoder, or if you're struggling because of temperature range, you might gravitate towards a resolver versus an encoder. So let's talk about steppers versus servos for a minute. So a stepper motor is really a set of magnets that are kind of sandwiched on each other and a couple of windings in it. And to make a stepper motor rotate, if you look on the left view here, this is when it's in the 0-degree position and the top and bottom windings are activated. And then if you switch the windings to the ones that are horizontal, it goes one full step, and now that north pole of the magnet is lined up with that winding there. So that's how you rotate stepper motors. And there's typically no feedback when you're, you can mount an encoder to a stepper motor, but it doesn't really change the stepper motor behavior that much. So let me talk about that just a little bit more here. One other mode of operation for stepper motors is half-stepping mode. So if you, instead of activating one winding and then the other winding, if you activate them both at about 50%, then that stepper motor rotor will go halfway between the windings. So they call that a half-step mode. And what happens with a stepper motor is that you can kind of imagine as it goes between those different steps, each time it changes position, it actually kind of oscillates like a spring when it goes into that position. So stepper motors don't have real smooth motion as they're settling into position. There is some oscillation. And one way manufacturers deal with this is when they create a motion profile for a stepper motor, they assign a certain low speed that they don't operate at that speed, so that they just transition past it to avoid the areas of resonance. So if you see base speed referred to with the stepper motor, that's what they're referring to here. And then there's a third mode of operation for stepper motors that you might have heard of called micro-stepping. And what that is that instead of turning the windings on at 50% each and doing a half step, they increment the power going to each winding in much finer resolution so that they get a whole bunch of small steps between each full step. But there's some things to keep in mind about that. When a stepper motor stalls, when it loses position, it actually always flips a full step or has a tendency to flip a full step. So when you're using micro stepping, and you might be inclined to think, oh, if I lose position, I'm only gonna miss a couple of small micro steps. That's usually not the case. It's usually gonna flip out a whole step. Also, full motor torque is not developed on every micro step. So you don't get the full stepper motor power on each micro step. So you might try to increment it 1,000 micro steps, and it might only go 50 micro steps because you didn't get full motor torque. That's different than a servo motor where you can develop full motor torque for any number of commanded steps. The other thing to be familiar with if you're using stepper motors with micro-stepping is that micro-stepping is not linear. So you can't treat it like a high-resolution encoder. The micro-steps are not necessarily evenly spaced out. So if you do need high resolution, you're usually better off to go with a servo motor with a higher resolution encoder. Then there's the common kind of stepper motor is a hybrid stepper motor, and that's usually a style that has 200 steps per revolution instead of the drawing that I was showing previously. So I just wanted to show you what that looks like. It's just a different style of rotor and motor to give you more poles and more steps per revolution. The good thing about micro-stepping is that micro-stepping reduces the oscillation that occurs with stepper motors. So you do get smoother operation. So last thing about stepper motors is that you may have seen the ability to connect them in series and parallel. So this is just connecting the windings two different ways, where one way gets you increased torque but lower speed, and the other is vice versa. So here's the torque speed curve for stepper motor connected in series, kind of the purple one, and then one connected in parallel. So it's just something to consider if you're applying stepper motors is, which motor do you use and how do you connect it? So now that we're looking at the torque speed curve, the next question is, well, how does this compare to a servo motor? And here's the torque speed curve of a size 34 servo motor compared to a size 34 stepper. So a size 34 servo motor, you get much higher RPM, up to 5,000 RPM to the rated speed, and you get significantly higher torque. So pound for pound in the same package size, you'll generally get a lot more performance out of the same size servo motor. So to wrap up the section on steppers versus servos, stepper systems cost less. They're usually about 30 or 40% less than a servo system. They don't use servo loop feedback, although they can use an encoder on them to verify the position. It's not a true servo loop where it increases the torque to get it into position. It's just, if it's not in position, you can try commanding more steps, but that won't increase the power going to the motor. So use caution regarding the accuracy of micro-stepping systems. And they have less power and speed compared to the equivalent system. And you should also use caution when applying them at low speeds, just because of the resonance that occurs. So that's steppers versus servos. So let's spend a few minutes talking about the magic black box of PID tuning. So PID stands for proportional integral derivative. And it's kind of a set of equations that are implemented in servo drives to help control them. Proportional means that you provide a correction that's proportional to the error. Integral means that you apply a correction that's proportional to the error summed over time. So the longer time you have an error, it continues to sort of accumulate that and apply more and more correction. And then the derivative term means that you apply a correction that's proportional to the rate of change of the error. So if the error is increasing at a high rate, your derivative term can damp that and cause it to resonate less. So let me show you a picture of what this looks like in a simple block diagram. So your basic feedback loop looks like this with an amplifier and a motor and encoder and the position feedback coming back here, and it gets digitally summed with the position command. And when you add in a proportional term to the system, it looks like this. So in this system, if your error is 100 counts and your proportional term is set to like 2, you multiply that times 2, then your correction would be 2 times that, so you would force it to correct at a higher rate. Then when you enter in, add the integral term, now also if your error is 100 counts, but it's 100 counts every millisecond, the integral term continues to sum that up and apply more and more correction the longer that you're out of position. And then the derivative term is similar in this loop, except that it applies a correction that is proportional to the rate of change of the error. So how do you tune these? Oh, one sec, I just want to check the chat here, see if there's, oh, I can get to that later, okay. So let me tell you how you tune these. So the quick and dirty way to tune these is set all your gains to 0, increase the proportional gain to the point where the system begins to oscillate, then reduce it enough to stop the oscillation, add an integral term until you eliminate the steady state error, and add the derivative term to reduce the overshoot. So I'll just quickly show you some graphs of how this works. So you start out, if you have all your gains set to 0 and then a low proportional gain, your command and actual position are far away from each other. And then when you add in more proportional gain, the command and position gets closer to the, the feedback position gets closer to the commanded position. Then if you add integral gain down here in the bottom, you can see now you eliminate the steady state error, but you get some oscillation. And so then you add derivative gain down here on the bottom right, and that damps out the oscillation. So that's the quick and dirty way of tuning PID loops if you have to tune those on servo systems. Okay, so the last thing that I want to talk about here is just a few slides on using high power servo systems. So we've seen an increase in the size of actuators that are being used, and they're getting really big. And of course, with actuators this size, now you need big, big servo motors. So what Tolomatic has done is that a lot of times companies and organizations don't have access or experience with these higher powered servo systems. So we've partnered a little bit with NIDAC here and worked out some servo systems that work with these really high power actuators. So if you don't have access to high power servos, we can help you with that, and we work with them to size these properly. And I think one last point on these systems that I would make is that a lot of them are being applied in pressing applications where you move an actuator into a kind of a hard stop and you apply a very high force for a short duration. And that's using the peak force of these actuators, and that's what this graph is showing. And it's just kind of a word of caution to use care when we are doing these kind of pressing applications, that we size the actuator and the servo system properly to fit within its peak duration here. And we can help you with that here at Tolomatic too. So that's all I had on all this stuff here. Hopefully it didn't go too fast for you. So to recap, what we covered was DC drives and brushless drives, differences between coders and resolvers, steppers versus servo systems, PID loop tuning, and a little bit on applying high power servo drives and their peak torque duration.